Welcome back. In this lecture, we will introduce an important mechanism in nuclear reaction theory. It's called the compound nuclear reaction model. There are other models, but this is one of the earliest model for nuclear reaction. So we will elucidate this model in this and probably in a subsequent lecture. So how do you visualize this? This model was initially proposed or rather quantified by Bohr. If you remember, there are two contrasting model for nucleus. One is the liquid drop model, which imagines the nucleus to be like a continuum, like a liquid drop. The other is a nuclear shell model, wherein each nucleon behaves as if it is an independent particle. Okay, so that happens only when nucleus behaves like a dilute gas, whereas in the liquid drop model, it's like a condensed matter. Okay, so this model is more similar to the liquid drop model. Let's see the operational principles in this model. So first, the projectile hits the target nuclei and gets absorbed by the target nuclei. They form a compound nucleus, which is like an excited state of the nucleus. So after this excitation, there is a de-excitation of the nucleus via either a gamma photon, or there is a terminology called particle evaporation. This is an unusual terminology, but you should remember this is built on the liquid drop model, right? So if you have a liquid drop, you can imagine part of the liquid to evaporate. So that's the basis for this jargon. So we'll illustrate this with a particular schematic. So there is a target nucleus, a projectile A. Before it forms the products of B and some emission, there is a compound nucleus that is formed. Okay, so in a way, you can consider this like a separate reaction, this like a separate reaction. Okay, so when things are independent, you can write the overall cross section for A going to B as a product of two reaction cross section. This reaction cross section corresponds to this nuclear reaction, and this cross section corresponds to this nuclear reaction. So we have already used this terminology called excitation energy. So we'll elaborate that a little bit. So this is the energy of the center of mass. We mentioned that the equations become simpler in the center of mass frame. So this is the energy, kinetic energy in the center of mass frame. This is the energy that is released in the nuclear reaction. For example, if you take up a particular reaction, let's say aluminum is exposed to the projectile, neutron is a projectile, it forms an excited state of aluminum. This will get de-excited, and then it would lead to, let's say, this particular reaction, okay, this particular products. So you can calculate the Q of this reaction. So this corresponds to the weight, this corresponds to the weight of the neutron, this corresponds to the weight of aluminum, de-excited aluminum. So the Q of this reaction is 7.72 MeV. So plugging this value into this equation, supposing you have a 1 MeV neutron, this is the energy available with respect to center of mass coordinates. This is the reduced mass. All right, it's reduced mass times 1 MeV plus Q. Okay, so that is Q is provided here. Okay, so E star, that is the excitation energy, is 8.68 MeV. Okay, so this is just a example for a particular reaction. So there is an important question. It's a very physical question. So this excitation energy, where is it stored in the nucleus? Is it stored in part of the nucleus, or is it more or less stored in the entire nucleus? Why is this important? Supposing it is stored in some part of the nucleus, then the chances of that part of the nucleus being in a higher energy state is possible, right? You can visualize that. To answer this question, this was a very important question. Where does this energy go? This excitation energy, where does it reside in the excited nucleus? Was an important question, and there were a lot of arguments to settle this question or to view this question in a better manner. One argument is the following. If you remember, we had discussed something called separation energy of the nucleon, right? So this is the energy to remove the highest energy nucleon or to remove one nucleon from the nucleus. We can remove either a neutron or a proton. So typically what was observed was that, this is from one of the earlier lecture in this course. So this graph is from one of the earlier lectures. What is noticed is the separation energy scale is typically less than E star. Okay, so E star is this quantity. If it is less than E star, one way to argue is this E star can be used for removing one of the nucleon. Okay, but that doesn't happen. Which seems to, I mean, that would have happened if E star goes exclusively towards one particular nucleon, removing that nucleon, but that doesn't happen. So the general idea was that because of this observation, the general idea was the projectile energy gets equilibrated in the compound nucleus. So it is nucleated in such a way that the history of formation of the compound nucleus is lost. We will see what we mean by this in a subsequent slide. That is, you may use a variety of projectiles to excite the nucleus. Supposing you have excited the nucleus, the excited nucleus really forgets how it was excited, okay? Because supposing there are more than one way of exciting this nucleus, the excited nucleus just forgets which kind of excitation was used to get the nucleus to that level, okay? So we'll also see what is the evidence for this statement. So then, once you form the excited nucleus, the de-excitation is a slow process. Why is this consequential? In this time, the energy gets equilibrated into the entire nucleus. Supposing de-excitation was a fast process, then the spread of energy into the entire nucleus would have not been possible, would not be possible. But because the de-excitation is a slow process, before the nucleus gets de-excited, the entire excited energy gets distributed into all parts of the nucleus. So, in a way, the formation of a compound nucleus and the de-excitation are almost two independent events. Okay, you can treat this differently and this differently. So let us also look at some of the other arguments. So typically what is observed is the lifetime of a compound nucleus is this time scale. Okay, it is possible to measure this quantity using some spectroscopy. You can measure this. The velocity of neutron, the 1 MeV neutron, is this given by this quantity. You know the nuclear size. So the question being asked is that how long does a neutron traveling at this speed take to cross this dimension? If you look at that, you divide this by this, it gives you a time scale. This time scale is much smaller than this time scale. Because this time scale is much smaller than this time scale, the idea is that this neutron sloshes inside the nucleus many times, which makes the energy get distributed into the entire nucleus. Okay, so the most important thing is you have an energy velocity scale from the energy scale. You have a length scale, get a time scale. This time scale is much smaller than this time scale. Okay, so there are a lot of sloshing around of this neutron before something happens to the excited nucleus. That's the argument. There's another argument to suggest that this excited nucleus energy is distributed into all parts of the nucleus. Another important experiment is this following. Again, this was done by Ghoshal, so who was introduced in the previous lecture. So it's a very interesting experiment. So supposing there are two ways of forming this nucleus, and once you form this nucleus, it gets decayed via three possible routes. Okay, so what are the two ways? One is that you form this nucleus via accelerated proton or via helium. Okay, so you start with nickel, hit it with helium. This is an alpha particle, hit it with alpha particle and get to this nucleus. Take copper, hit it with proton and get to this nucleus. Okay. So what is the question being asked? Supposing this nucleus forgets how it came to this point. Okay. Then the possibility of or the decay pathway is independent of how it reached, okay, this point. That is, either it doesn't matter whether it reaches this nucleus via this pathway or it reaches via this pathway, it continues to decay in a very similar manner, okay? So that is an important evidence that this compound nucleus forgets the way it was excited into forming a compound nucleus. Okay, so independent of how it was excited, the decay pathways are very similar. Okay, so what was measured was the reaction cross section for, let's say, this to this divided by you're calculating or you are measuring the ratio of two cross sections. Okay, so here this cross section is indicated by this and this. This cross section is indicated by this and this. Okay, so whether you get to this via alpha or get to this via the proton as a projectile, the ratios are the same. Okay, this seems to, that is, the ratio of the channels seems to be the same, which indicates that this compound nucleus has forgotten how it was excited. Okay, so this was again a very important experiment done by this famous Indian nuclear physicist Ghoshal. In the next lecture, we will look at certain additional features of compound nucleus reaction theory. Thank you.